Hello guys, welcome back to my channel Gamma Die Gamma. So in the last video we did the first 5 problems of MIT Integration B 2020 final. I'm going to do the remaining 5 questions. So let's get started. Continuing from last time, so that makes it question 6. Question 6. We have the integral, the indefinite integral, which has x squared minus x times square root of x squared minus 1 in the denominator. Now, just looking at the form in the denominator, you should anticipate that the substitution we're going to do is a trigonometric one, namely x equals secant theta, because secant squared theta minus 1 will be tangent squared theta, which will simplify things nicely. So dx is secant theta tangent theta d theta. I therefore becomes sec theta tan theta d theta divided by secant squared theta minus secant theta, and then the radical term becomes tangent theta. I'll just resize this a little bit so that it's clear. Okay, what we can do here is cancel the secant theta from numerator and denominator. So we just have a tangent theta divided by secant theta minus tangent theta d theta. What we can do here is we can multiply and divide by this conjugate term of the denominator, which is secant theta plus tangent theta, because we can use difference of square identity to really annihilate the denominator effectively. Because secant theta minus tangent theta times secant theta plus tangent theta will be secant squared theta minus tangent squared theta, which is identically 1. So the denominator is completely gone now. We have tangent theta, secant theta plus tangent theta. Maybe I'll just write it down because I might be going too fast right now. So secant squared theta minus tangent squared theta d theta, which just means the denominator has gone away, and we have, let's see, secant theta tangent theta d theta and a tangent squared theta, which I will choose to write as secant squared theta minus 1, because this helps us to integrate everything nicely. Secant theta tangent theta is just the derivative of secant theta, plus secant squared theta is the derivative of tangent theta, 1 is the derivative of theta, and we also add a constant of integration like that. Now, since this was indefinite, we need to back substitute for secant theta, and we need to sort of get x. So secant theta is x, so we have this. Tangent theta is secant squared theta minus 1, so that's x squared minus 1 under square root will be tangent theta precisely. So we have square root of x squared minus 1 minus, well, theta is just the inverse tangent of whatever tan theta was, so that's x squared minus 1 under square root plus c. There we go. That is the final answer, and we've solved this indefinite integral. So moving on now to question 7. We have I to be the integral from 0 to infinity of the inverse tangent of x minus the inverse tangent of pi times x divided by x dx. Now, I think I've done a similar kind of integral in the past, in the early days of this YouTube channel. If you've been a regular viewer, you might realize it, you might recognize it. I might have done one for the hyperbolic inverse tangent, But regardless, one of the most powerful ways of doing such questions is using Frulani's theorem, which basically involves integrands like this. One could also use a Feynman technique. I mean, I don't know if they really expect us as participants, potential participants in the MIT integration B to know Feynman's technique, or you can also use Taylor series expansion for the inverse tangent if you remember it and you know how to use it and have to work with infinite series. But I'm going to use the good old fashioned integration by parts. So none of these fancy non-elementary techniques. So when I say integration by parts, we can't really integrate the inverse tangent. We have to do the 1 over x. So you have natural log of x upon integration. The numerator remains the same. It's a pretty long expression. Evaluated at 0 and infinity minus integral from 0 to infinity. Natural log of x 1 over 1 plus x squared. This is differentiating the first inverse tangent and then the second. 1 plus pi squared x squared dx. Now, in all sincerity, the hardest part of doing this question was actually doing the first term in this integration by parts result. The limits. The second term was pretty much just a case of substitution and it works out. So let's do the limits. Let's do the 1 at 0. It's not really plugging in, non-trivial plugging in anymore, because natural log of 0 goes to minus infinity and the difference of inverse tangents goes to 0. So we have 0 times infinity, which we should be able to write as one of those L'Hopital rule indeterminate forms. I'm doing nothing fancy, it's just L'Hopital's rule. Limits 101 probably. So I have inverse tangent of x minus inverse tangent of pi x. I'm going to keep that difference as it is. I'm going to put the natural log in the denominator. So the natural log is going to have a power minus 1. Or maybe I should use a slightly better notation, because we can also use that notation for function inverses, not multiplicative inverses. And now we really have a 0 over 0 situation and we can use L'Hopital's rule. So I'm differentiating the numerator and the denominator to obtain 1 over 1 plus x squared minus pi over 1 plus pi squared x squared divided by negative 1 natural log of x to the minus 2 power along with the 1 over x. This is the chain rule in the denominator. Well, how is this helpful? That's because look at the numerator. If you take the limit as x goes to 0, we're going to have 1 minus pi along with the negative. So that's pi minus 1. That sort of does not depend on x anymore, and we can always take it out. We can always factor it out nicely because it's not going to result in any indeterminate forms of zeros or infinities. Nothing funny is happening over there. It's finite. What's the funny thing that's happening is the stuff that is obtained from the denominator. So that's the x and then the natural log squared of x. This is causing the funny business. So we can again use L'Hopital's rule. Why? We can again write this in an indeterminate form that is permissible. Natural log squared of x or 1 over x. This has become infinity over infinity now. And we can really evaluate this. 2 times natural log of x minus I think 1 over x squared. Yeah. Limit as x goes to 0. We can again do a L'Hopital's rule. 2 times 1 minus pi. Limit as x goes to 0. Natural log of x over 1 over x. Which, if you sort of do L'Hopital's rule one more time on such an expression, there's a 1 over x, I forgot. if you do L'Hopital's rule one more time on this guy, it's actually going to go to 0 because natural log will have a 1 over x contribution and the denominator will have a 1 over x squared. So it's just going to be minus 2 times 1 minus pi, I think, and then limit as x goes to 0 of x. So that just goes to 0. So there we go. We've actually gotten rid of the 0. At 0 it goes to, well, 0. So that's nice. What about the infinity? It's a little, we have to do one more extra step that's perceivable compared to the 0. So we have limit as x goes to infinity of natural log of x, inverse tangent of x minus inverse tangent of pi x. Now what I'm going to do is I'm going to use a change of variables. U is 1 over x such that as x goes to infinity, u will go to 0. When I do that, everything changes. Limit as u goes to 0, natural log of 1 over u, inverse tangent of 1 over u minus inverse tangent of pi over u. We have minus limit as u goes to 0. Using the natural log properties, it's just natural log of u, along with the difference of these inverse tangents. I will not waste more time. I will just repeat the process as before. The natural log can go in the denominator as 1 over the natural log, and then we can use L'Hopital's rule to directly get limit as u goes to 0, u squared minus 1 over u squared. I'm using chain rule because I have to differentiate the inverse tangent of 1 over u squared plus 1 minus pi u squared times negative 1 over u squared over pi squared plus u squared. I'm skipping over lots of algebra. Yeah, and then all of that is being divided by the denominator's derivative. So that will again result in a natural log squared of u times u. That's basically the term we had before. This natural log of x to the minus 2 and 1 over x in the denominator become this in the numerator. Stuff cancels out nicely, and there's an evident symmetry in these things because we take the limit and we sort of pull out the part that is not causing any problems, i.e. that is not going to 0 or infinity, thereby resulting in an indeterminacy. The indeterminate part is just natural log squared of u times u, the same as before. And we know I'm not gonna go through the 3 L'Hopital rule steps, but we know this goes to 0 from before. So there we go. There's a symmetry between the 0 and an infinity, which is evident by this change of limits here. So at infinity also this thing goes to 0 and it's gone. So all we're supposed to be concerned with are the integral minus natural log of x and all that other stuff. So minus integral from 0 to infinity natural log of x over 1 plus x squared dx plus pi times integral from 0 to infinity natural log of x over 1 plus pi squared x squared dx. Now on the second integral I can do a change of variables. Y is pi x, so dx is dy over pi, or pi dx is dy. The first integral unchanged. I'm not solving it yet. I'll show you why. Upper and lower bounds are the same. We have natural log of x is y over pi. That remains 1 plus y squared, and then we just have a dy. The pi goes away. This is really nice because first guy as it is, we can use the natural log properties on the second integral to get natural log of y over 1 plus y squared dy minus integral from 0 to infinity natural log of pi over 1 plus y squared dy. Now, since it's a definite integral, doesn't really matter what variable of integration there is. So these both things cancel out because it's the same range, same domain of integration as well as the same integrand, just a difference of variables. So it's just the same integral. Now in this guy, natural log of pi is a constant which comes outside. Integral from 0 to infinity, dy over 1 plus y squared is going to be an inverse tangent of y at 0 and infinity, which is just going to be pi over 2. So this is the final answer. And yeah, that's how you solve this integral. And there we go. So I equals the integral of square root x times natural log of x plus 1 dx. This is again a classic case of integration by parts. We're obviously going to integrate the square root x and then differentiate natural log, because you can't really integrate a natural log without much hassle. So 2 over 3 after integration, 2 over 3x to 3 halves, natural log of x plus 1 minus 2/3 integral x to the 3 halves divided by x plus 1 dx. This is just integration by parts, nothing fancy. Well, the first term, nothing happens here. I'm not putting the absolute value sign on the natural log because it's sort of assumed that it is inside the domain of convergence. What we can do is x to the 3 halves is x times square root x. So that x I can write as plus 1 and minus 1. That's essentially adding zeros. That doesn't do much. And x to the 1 half, because x times x to the 1 half is x to the 3 halves. How did that help? Because we can use linearity, split the second term completely. So we have 2 by 3. We're gonna have x plus 1 over x plus 1 square root of x dx plus 2/3 integral of square root x over x plus 1 dx. This goes away. The first term is annoyingly sticking around. I have to keep writing it. Minus 2/3 and integral of square root of x. So that's going to be give me 4/9 x to the 3 halves plus 2/3. Let's use a substitution here. X is u squared. So dx is 2u du. If I do that, I have 2u squared here divided by u squared plus 1 du. And again, this is beneficial because let me just paste this. Because again, we can sort of factor this out nicely. 4/3 u squared plus 1 over u squared plus 1. So all I've done is a plus 1 and a minus 1. So minus 4/3 du over 1 plus u squared. Everything else is the same. So I'm taking the liberty of just pasting it out like that. Plus 4/3 u, because this became 1. Minus 4/3 inverse tangent of u because of that. Plus it's important to keep the variable as it is. So, not writing an x in place of u, because we have to still back substitute big time. I mean, it's the back substitution is not really that bad because x is simply, let's see, x is simply u squared. So we have u is square root of x minus 4/3 inverse tangent of x to the 1/2 plus c. That's the big long answer, but that is the answer. So there we go. And there we go, we move to the penultimate question, question number 9. Integral 0 to pi x times sine to the 2020 of x divided by cosine to the 2020 of x plus sine to 2020 of x. The thing with these Olympiads, these competitions for a given year, is that they always have questions like this where the year is part of the calculation. Okay, so just looking at this question without even doing anything, our natural instinct tells us this question is going to involve symmetry heavily. It's going to heavily involve symmetry. So first thing what we can do is we can change x to basically be upper limit plus lower limit minus the original variable, which is x. So x changes to pi minus x. You can try plugging this. You can try doing a u substitution where you have x prime equals pi minus x. But I'm just skipping steps. This is just by symmetry, and there's a nice property of definite integrals. You can just change everything directly because the limits, the dx factor, everything just works out naturally. Sine of pi minus x is sine x, so that doesn't really matter. Sine stays the same. Well, the cos will actually become a negative. Cos of pi minus x is negative cos x, but that doesn't matter because 2020 is an even power. You're still gonna have cos 2020 of x plus sine for 2020 of x dx. The beautiful thing about this procedure that we just did is this linear term x disappears. It cancels itself out. Why? Because this is also I. Because if you add I and I together, which is basically the top line and the bottom integral, the x goes away and we just have this residual pi outside, and then everything else is the same. So we have sine of 2020 of x over cosine to the 2020 of x sine to the 2020 of x dx. Now to really destroy this question, we have to split the interval of 0 to pi to 0 to pi over 2 and pi over 2 to pi. That's because we can use the complementary angles property. If you don't know what I'm talking about, you'll see in a minute what I'm saying. I will make a copy of this integrand because I will need it. I'll need to paste that again and again. Maybe I'll move the dx a little over there. Plus, maybe I could bracket like that. Well, pi over 2 to pi, and then the integrand, which I will nicely paste here. Probably move the dx a little bit over there. This is really nice. You might not see it, but you see the second integral. We can really use a u substitution over there. We can really use a u substitution over there. The second integral, what we can do is we can set y equal to x minus pi over 2. dy is dx, so we're fine on that front. So pi times integral from 0 to pi over 2. I will copy the integrand like this. Plus pi times, if we use this substitution, upper and lower limits are going to be 0 and pi over 2 respectively. The sine, however, becomes a cosine while the denominator remains the same, because sine and cosine basically just switch positions, and that's fine because addition is commutative. So sine to the 2020 of x, cos to the 2020 of x. How is this? Because of complementary angles. Cosine pi over 2 is sine, cosine pi over 2 minus x is sine of x. Sine of pi over 2 minus x is cosine of x. That's basically why I split the interval up. This is nice because you can add both of them. They have the same interval. And you're going to have the same thing in the numerator as well as the denominator. So that's just going to be 1. Integrated from 0 to pi over 2 dx. Maybe I should have a y here, for sake of continuity or convenience. Y doesn't really matter because definite integrals, doesn't matter what variable you have. This will give us pi squared over 2, but let me remind you, this is just 2i. Alright, because we had to add up to get rid of the linear x. So 2i is pi squared over 2. This implies that I, dividing both sides by 2, is pi squared over 4. That is precisely the answer. There we go. This is pi squared over 4. And now we move on to our ultimate question. Our last question, basically. And it's always a pain to choose what color. Maybe I'll just go for white. Number 10. I is integral from minus infinity to 0 cosine of theta times x divided by cosine to the x of theta dx. Well, this might require some thinking, maybe like half a minute or 1 minute of thinking, and you will realize that integration by parts is the best strategy, and it is wise to integrate the numerator because it's just a regular sort of compound angle trigonometric function compared to the denominator, which is actually an exponential function. Why is it exponential? Because the variable of integration is in the power. X is in the power. So, which means we'll have to integrate the numerator both times. So you're going to have sine of theta x divided by theta for reversing the chain rule, and then the other term remains the same, evaluated at x goes to 0 and x goes to negative infinity. I'm just writing x because I don't want any confusions between a theta and an x. You might forget that the variable of integration is actually x. Minus integral from minus infinity to 0. Sine theta x over theta remains the same. But now what we have to differentiate cosine to the minus x of theta. We differentiate that, the minus comes down, this becomes a plus. Cosine to the minus x of theta remains the same, which is cosine to the x of theta in the denominator. But we also have to multiply by the natural log of cosine of theta by the chain rule. This is basically differentiating an exponential function. Please refer to a formula sheet if you sort of don't know, or you can maybe derive it from some limit properties of these things. One thing we know for certain, theta cannot be 0, because if it is 0, the denominator of the first term, whose limit we have to, or which we have to evaluate at upper and lower bounds, that term will basically blow up, and that's not really a good idea. So we have this assumption, a perfectly valid assumption. At 0, sine of 0 is 0, and well, cosine of whatever angle to the 0th power is always going to be 1. Anything to 0th power is 1. So at x goes to 0, the entire thing goes to 0 because sine is going to 0. Now at minus infinity, it's not really that clear. So that's why I'm saying let's see what happens to absolute value of cosine of theta. Well, it's between 0 and 1, but the thing is we're not going to include 1. Why? It's because theta is not equal to 0. Cosine of 0 is 1. Cosine won't be able to reach its value of 1, and we're considering theta to be sort of trapped in that one cycle. So it can't really also be 2 pi. So it's, I think the theta belongs to 0 and 2 pi, where 0 and 2 pi are excluded. I don't remember the exact condition. They probably didn't specify it well, or maybe they did. I'm not sure. They probably didn't. Mostly they didn't. But that's what the condition for theta is, so that this is guaranteed. And why is this necessary? Because if we raise this entire thing to an arbitrary power x, where x is some number that's really let's going to infinity, that's basically really large. If we have something that's in the 0 to 1 range raised to a really high power, it's always going to be 0, right? Because you can represent any number between 0 to 1. You can approximate it. I mean, these are going to be irrational, but you can always approximate it by some rational that looks like m over n, or rather just 1 over n, because it's between 0 and 1. And as the power it's raised to goes to infinity, it's going to go to 0, right? This is just simple limit observation. So that means x going to negative infinity is basically saying the denominator going to negative infinity, which means the cosine goes in the numerator and is raised to infinity. So basically this condition here holds, the condition that we were looking for basically, or we were analyzing. This will hold because the cosine will go in the numerator, and then cosine is bounded like this, and theta is in that given range. So this will also go to 0, because 1 over n raised to some infinite power is going to be 0. So it's all of this is gone. It's gone. It's really gone. So all we're left with is let's see, what we can do is we have this integral. We can do another integration by parts. Again, same thing. Integrate the denominator. Natural log of cosine is independent of x, and it comes out along with the theta factor. We're going to have, let's see, a minus, because we integrate a sine now, and a theta squared. We're going to have a cosine theta x divided by cosine to the x of theta. This is just integration by parts on the second guy, on the integral that remained. X going to 0, x going to minus infinity, minus integral from minus infinity to 0, cosine theta x, theta squared. Well, the two minuses, one from the integration and one from the differentiation, will cancel off. We're just left with the natural minus from the integration by parts procedure. We have a natural log squared of cosine theta d theta right here. Now at infinity, the same argument as before holds. Because the cosine of theta x is just going to be oscillating. It won't really contribute much to the magnitude, so as to say. The denominator will basically repeat the thing, the point here. So it's gone at negative infinity, it's gone to 0. At 0, the denominator goes to 1. Anything to the 0th power is 1. Cosine of theta times 0 is also 1. So we have minus natural log of cosine theta divided by theta squared minus, well, the natural log squared cosine theta comes out along with the theta squared, and then what will remain is cosine theta x divided by cosine to the x of theta, which is basically the integral we started with. It's just this integral right here. So that means we have minus natural log of cosine theta over theta squared minus natural log squared of cosine theta over theta squared times capital I. We can make capital I the subject of this equation, so that we get 1 plus natural log squared of cosine theta divided by theta squared to be equal to minus natural log of cosine theta over theta squared. The theta squared will destroy on both sides of this equation to give us minus natural log of cosine theta over theta squared plus natural log squared of cosine theta, theta belonging to that range, because we cannot have some issues going down in these natural logs. We can't have them going to 0, so maybe the restriction is not 0 to 2 pi, it's some disjoint set probably. Anyways, this is the answer. This should be the answer. Pretty confident it is. The only key observation here was to realize since we have a trigonometric function in the integration by parts, we need to repeat it again so that we regenerate the original integral like this. And this usually happens when you have a trigonometric function involved in an integration by parts procedure, and then it was pretty straightforward. The only tricky bit was probably differentiating an exponential function. So there we go, that's it for this video. Please like and subscribe to my channel. Peace out and stay tuned for more stuff.